So let's talk about domain number 4 now, communication and network security, or designing and protecting network security. So our key areas for this domain: apply secure design principles to our network architecture, securing our network components, securing communication channels, and preventing or mitigating network attacks. So in our first key area, applying secure design principles to network architecture. A lot of things going on in this key area that we really need to discuss. We need to go back over the OSI model and the TCP/IP model to make sure you're familiar with that. If you don't have any experience with that, maybe this will be a good stepping stone for you. We don't really dive super deep into the OSI model and TCP/IP model, but it's a good overview. Those of you that are familiar with it, maybe you've taken some networking courses in the past, maybe this will be a little refresher for you and it'll kick back in there for you. We'll talk a little bit about IP networking and how traffic goes from point to point. Talk about some of the multi-layer protocols that we have out there, our converged protocols that are very popular nowadays. Software-defined networks, we have those all over the internet. We're going to discuss those. Talk some about our wireless networks and our wireless networking. A little bit about security when it comes to wireless networking. And then cryptography used to maintain our security of our communications. So quite a few things we need to talk about in this one key area. So let's start with the OSI model. Now the OSI model, the Open Systems Interconnection model, was created by the ISO folks, the International Standards Organization. Now this is a model that uses layered architecture to standardize the levels of service and the interaction types for networked computers or our networked systems. And you can see there I put out 7 layers. So there's 7 of them that we need to know: application, presentation, session transport, network, data link, and the physical layer. So in these 7 layers, we can kind of break these 7 layers out. The top layers could be considered like application layers. The top 3, application, presentation, and session. And those are the ones, when it comes to networking, we know they're there, but they're not really concerned with that as far as the networking. So we're probably not going to pay as much attention to those in this networking type chapter or domain either. Just know that's where the data is coming from, right? The data works its way down, and we want to get down to the physical layer. Transport layer, network layer, data link layer, and the physical layer are those data link layers that we have down at the bottom, the last 4 layers. And those are the ones that we're going to be mainly concerned with when it comes to networking. Now that transport layer is going to be responsible for, say, TCP and UDP, the reliable delivery of our information. The network layer is where IP is going to be living. The data link is where our MAC addressing. And the physical layer is, think about like that as the cabling, the wires, the network interface cards. So let's take a little closer look. Real briefly about those upper layers, right? Those application layers I was mentioning. The application layer itself, the very top layer, layer number 7. That is our user interface, right? That is the underlying application of what we are using, like HTTP or SMTP or Telnet. Then below that, we have a presentation layer of how that application is going to be presented to us as end users. Is it going to be a picture? Is it going to be words or graphics? Or is it going to be music or video? So that's all how it's shown or presented to us as end users. We can also have some encryption and compression take place at this layer as well. So for example, if you take or think about, say, a GIF, a GIF file, picture file, or a JPEG file. You know, a GIF file is 256 colors. All right, quite a bit of colors, right? Probably more than I can see. But a JPEG is 16.7 million colors. A lot more colors. You would think this file size is a lot larger, but it's not. A JPEG is actually smaller than a GIF traditionally because it is compressed. So that's just an example of where this takes place here on the presentation layer. Then we have a session layer. Now, this session layer is establishing, managing, and terminating communication sessions between the different entities. So between the different applications, if you will. So those three layers, that's probably all we're going to mention that. Just know that's where the data comes from, right? We create the data. We're using an application, typing some data out. It moves on down, and eventually it's going to get to the transport layer. And then when we get to these lower layers, we're going to have to add information on there. And this information we're going to add on is addressing information. And we're going to see that throughout this whole area. So now let's get to the meat of it, the transport layer. So we have our data and we're working our way down the stack. And when we're working our way down the stack, by the way, we're putting things on there. That's called encapsulation. We're wrapping data, wrapping information around our original data, I should say. So at the transport layer, what we need to keep in mind, key terms, key things we need to think about is TCP and UDP, Transmission Control Protocol and User Datagram Protocol. These are the protocols that are going to be responsible for the delivery of our data. So it is reliable or unreliable delivery or best effort. TCP is a reliable protocol. And we're going to see that here in just a little bit when we talk about the three-way handshake. UDP is more of a best effort protocol. So TCP makes sure and it says, hey, are you there? I'd like to communicate with you. And if I acknowledge that, he was so great. So we've established this connection. So now let's start passing some information. UDP doesn't do that. UDP says, I got some information. It's supposed to go that way. Away it goes. And it doesn't really care if the other end gets it or not. It doesn't have any mechanisms in place to say, hey, did you get that? Oh, you did? Let me resend that for you. It just sends it and forgets it. Now we have the network layer. Moving on down. We're at layer 3 now. Network layer has a pretty important job as well. This provides our logical addressing. Now, logical addressing is another name or term for our IP address because logical, it can change, right? It's not hard-coded on anything. So logically, we can use it in programming. We can use it in our development, but we can put this on a system, right? We can change our IP address. So that IP address is used for routers, or by routers, I should say, and they use that for path determination. Because they're going to see that information come into the router. They're going to look up at a header, and we're going to see an IP header in a little bit. But they're going to look for the destination IP address. And they're going to say, okay, that's the destination IP address. There's the subnet mask. It belongs to this network. And it's going to look in its routing table. And it's going to say, okay, oh, it matches right here. Okay, let me go see if there's a better match. No, it doesn't. So we're going to go out whatever exit interface that entry in the routing table says. Well, that's this interface over here. So it will take that information off of this interface, switch it over to this exit interface, and send it on its merry little way. And more than likely, it's going to hit another router, and that router will do the exact same thing. Possibly. We're going to talk about some technologies that may change the way they act. But for the most part, that's how it's going to behave. It will bounce from router to router until it gets to its destination. At least that's what we expect to happen, right? Sometimes things happen and it doesn't end up where it's supposed to go. But for the most part, it does a really good job. So at the network layer, you need to think IP addressing, internet protocol. We move on down to the second layer, the data link layer. This one is combining bits into bytes and bytes into frames now. So keywords at this level, frames, MAC addressing, hardware addressing, Ethernet addressing. All right, those last three are all synonymous. The hardware address, the Ethernet address, the MAC address, the network interface card address, they're all the same. They're not supposed to change. That's hard-coded on the network interface card in your system. This is also the layer of how information is delivered to the end system. It's not delivered by IP, it's delivered by MAC address. Now, we need to think of Ethernet here. We can think of 802.3, 802.2, HDLC, and PPP. That's high-level data link control and point-to-point protocol. We use those on our serial connections, say between routers on point-to-point connections. And then lastly, the physical layer down there at the very bottom, right? This is taking all that information and putting it out on the wire, out the network interface card, all the ones and the zeros, the highs and the lows, all those bits, and sending it on its merry little way. So it will move on and go down to the next router, switch, whatever device is next. More than likely it's a router or your default gateway to get out of your network. Now, taking what we know about the OSI model, all right, a little bit about the OSI model, we can look at that and compare it to the DoD model or the TCP/IP model. You may see them both ways. The TCP/IP model has 4 different layers instead of the 7. So the process application layer in the TCP/IP model lines up with the top 3 of the OSI model, the application, presentation, and session. Now we have a host-to-host layer in the TCP/IP model that does what the transport layer does in the OSI model. And then we have an internet, or you may also see that as network, lines up with the network layer in the OSI model. Same things are going on. We still have TCP, UDP in the host-to-host. We still have IP in the internet layer when it comes to TCP/IP model. And then we have a network access layer down at the bottom. That guy combines 2 of the layers in the OSI model, that data link and the physical layer. So again, in our network access, we're going to have MAC addressing, hardware addressing, Ethernet addressing. We might have something called LLC. You may need to be familiar with that as well. That's our logical link control. And that helps maintain the communications between layer 2 and layer 3. Now, something else that I want you to be familiar with are local area networks and different topologies of those local area networks. And I've got 3 listed out here: a bus topology, a ring topology, and a star topology. Now, a bus topology is an older technology, but this got us started designing networks. You know, when the bus topologies first came out, it was usually you would have some type of gateway, maybe at the edge of the building, or could be in the middle of the building, but more than likely it was more towards an edge where the connection from, say, an internet service provider was coming into the building. That's usually where we would put, say, a router or our default gateway. And then we would run one cable off of that. And at the end of that cable, we have something called a terminator. All right, so we don't have signal bounce back. Now, depending on if we're using thin net or thick net, depends on what type of connections we're going to have when we try to access the data inside of that wire. So let's just say we're using thin net, and we're going to have something called a BNC connector, where you push it in, you turn it a quarter turn, and it locks in, that British naval connector. So we could have the cable running down, say, the center of the building. And now we have all of our employees in there, and they take their end systems, their computers, and they hook up to that cable, right? So we would put a T connector in there and hook up our BNC connector, run the other end down to our computer. And that worked pretty good for a handful of computers. But the more computers that we put on this network, the more congestion we had. This topology is very prone to data collisions, all right, because everybody is on the same segment. There's no mechanism in place as far as like a switch that breaks up the traffic. We're all, if you will, like in one room. So if you was to take 2 people and stick them in a room, they could communicate pretty effectively. Right? I know to talk, you know to talk, I know to talk, you know to talk. But let's say we multiply that times 20 and we put 40 people inside of this room. Now, how effective can the communication be? Because you may have conversation over here, and a conversation over here, and over here, and over here, and eventually it gets louder and louder and louder, and you can't hear yourself think, much less hear the person across from you talk. So the communication is starting to become very congested. The network does the same thing. The more computers that we put on this bus topology, the more congested it gets. There is a mechanism in place that makes them take turns. All right, that's called CSMA-CD, Carrier Sense Multi-Access with Collision Detection. And what that means is they're going to listen, right? I'm going to listen to the line. There's no electrons going. It's clear for me to send traffic now. I'm good to go. So I'll go ahead and send my data. Now, also on a bus topology, everybody gets the data. Even if it's destined for one particular computer, which most of the time it is, everybody is going to see it. Now, when they get that information, they're going to look at the destination addressing and say, well, that's not my destination address. I don't need that. I'll go ahead and move that away. I'll drop it. I don't need that data. It's not mine. Now, the one that it's destined for will process the data and move on. But again, everybody hears that. Now, also with the CSMA-CD, if I'm listening and you're listening and nobody's talking, then we both think it's clear to send our information. And if we send it at the same time, we're going to have that collision because we have all that congestion. Well, as soon as that happens, that's when the CD part kicks in, the collision detection. Because it says, oh, there was a collision. I'm going to stop my transmission, I'm sorry, and I'm going to send out a jam signal. That jamming signal is telling everybody else on the network, ignore my last communication, there was a problem. Don't process that. Because in that collision, our data collides, it's going to be corrupted data, so it's not relevant information anymore. After they send out that jam signal, they're going to run a back-off algorithm. They're going to wait a few milliseconds and go ahead and send their data again. And all they have to do is be a part of millisecond. I mean, we're talking about electrons here. So it will send it, I'll wait, and then I'll send mine, and everything is good. But again, with two people, that's not a big problem, right? Have you ever been sitting in a car, riding with somebody for a while, and it's quiet, right? You have that awkward silence, and you're trying to think of something to say, they're thinking of something to say, and then you're listening, nobody's talking, so it's clear to send, just like the computers do. Then you say something, but they say something at the exact same time, and you kind of laugh about it, but then you wait a predetermined amount of time, and there's no really general rules about it. You wait a second, they wait a second, and then somebody starts to talk, right? So same thing we were doing on our bus topology. Now, ring topology is a little bit different, all right? You can see it's in a circle and a ring, and we've got things attached to it, devices. Again, we're using, could be vampire taps, could be BNC connectors, could be different types of connectors if it's a token ring topology, all right? Depends on how we implement this topology, but it's in a ring, and data usually only travels in one direction. In ring topologies, they're usually pretty fast, and there's usually little to no collisions because the data moves in one way. And if you have a token ring, right, think of it like a hall pass. You have to have the hall pass to do anything before you can communicate. So that token's going to go around the circle and start asking, do you have anything to say? 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 And if nobody has anything to say, that token just keeps moving until somebody is ready to communicate. Once somebody's ready to communicate, that token gets appended to the data. Now it knows where to go. It has a destination address on that data. So the token will go and say, oh, okay, this is destined for you. Here you go, process this data. Now we also have a star topology. And we can implement star topologies in a couple different ways. We can have it where we have an old technology or an older technology like a hub. And we're going to talk about those devices in a minute. But we may have a hub in the middle. And that's great. It kind of takes away some of the limitations we had with a bus topology. You know, in a bus topology, I'm not sure if I mentioned this earlier, but if there's a break in the line, the whole network comes down because we get that signal bounce back. Remember, I mentioned the terminator, right? We have to have the terminator on the end of that line so the signal doesn't bounce back and cause lots of communication errors. But if one of those computers gets unplugged and a terminator is not put on, or if there's a break in the line and there's not a terminator put in place, the whole network comes down. That doesn't happen with a star topology. Because that hub, there's a hardware device in the middle that acts as the terminator. So if one of those devices was to come unplugged, the whole network doesn't come down. Now logically, with a hub, it operates the exact same way though. It still has to listen. It has to see if anybody's communicating, and if they're not, it can send data because it's using that CSMA CD. It's still prone to collisions because everybody is in the same collision domain, just like they are in a bus topology. Now, if we was to take that star topology and put a switch in there, that changes the ball game a little bit. And I'm not going to steal the switch's thunder just yet because we're going to talk about those hardware devices in a minute. But when a switch is put in there, we're not using CSMA CD anymore. Okay? Because the switch doesn't need that. And we'll explain that a little bit later. Just know that is the difference. So it could be a logical star topology, all right? Or let me say a physical star topology, but it acts as a logical bus topology with a hub, okay? So remember that, keep that in mind when you're setting this up or when you're thinking about security for your networks.